Okay. My name is Mayank Vahia. I'm a scientist at Tata Fundamental Research. I spent a lifetime making satellite instruments. When I began my career, the only way you could do a good science experiment was to go coaxing, they would agree to let you fly. And that's how I began my career in 1986. We had a payload on the sky, on the space shuttle. And then subsequently, of course, by that time, Indian space program had become matured enough for us to do all our experiments here. So after that, we've never had to go back to America. Now, of course, we fly American instruments on Indian satellites.
Next year more so.
Sorry?
Next year more
Next
so.
year more so. Yeah. Oh, I'll just show you. We have sold some of our satellites and rocket and stuff like that. Okay, my last 2-3 years have been spent on a topic that's slightly different from this, which is on history of astronomy. But I'm not going to touch about those issues today at all. I'm only going to talk to you about this basic question of going to space. What does it involve? And why do you go to space? And whether we should, as a developing country, worry about going to space. So the first question to ask, of course, is why go to space? I mean, you can pretty well do everything from ground. For thousands of years, people have gone to have remained on the ground and done everything, so why go to space at all? First of all, whatever you do from ground, the sun rises and sets at the most 12 hours or even less. If you want to observe the sun, you cannot get more than 7 or 8 hours of good viewing time. If you want to see stars, you get no more than 7 or 8 hours of viewing time. If you want to observe the earth, and even if you do a balloon, you can't get more than 3 or 4 hours at a time, and even then balloon flips and all that. So essentially, if you want to look at your own earth for a long time, the best thing to do is to go to space. The second, of course, is communication. A point I hardly need to drive in these days of mobile phones and 1,000 channels of television and stuff. It's obvious that communication is something where you can do it. The third thing is that because light reaching into space is not easy to hide, you can always keep an eye on what your enemy is up to by looking at him from the space, so that we can get a pretty good idea about what is going on. And it's a nice cat and mouse game that goes on as far as defense is concerned. And astronomy, astronomers love space, simply because there is no perturbation from atmosphere, the skies are clear, you get sharp observations, you can observe for days together and things like that. And the last point, of course, is the sheer joy of space exploration. Whatever it is, having an Indian flag on the moon and its own charm about it. So, you want to do space exploration. Everybody wants to do space exploration. There are 130 odd countries in the world, and I'm sure 190 odd countries in the world, and I'm sure all of them would like to go to space and have their own space program. The question is, why do they not have it? And the question then is it easy to go to space? And the answer, as you can guess from the very fact that very few of us do that, is a clear no. And the question is, why is it a no? First of all, the costs are prohibitive. To launch a single gram of weight into space costs you about 1,000 rupees. And nobody flies a satellite which is 1 gram in weight. A typical satellite is about at least 1,000 kilograms in weight. So you're talking about 100 crore launch cost. A single, simple 1-ton satellite costs about 100 crores to launch. More likely, a typical satellite is about 2.5 tons. So you're talking about 250 crores for every launch. It's not something that most people can afford. It also, your instrument, whatever instrument you make, must fit on top of a rocket. The rockets are small, your instrument has to be small, and therefore the density of material that you need to put in, or the density of technology that you need to put in, is prohibitively complex. You need to get the whole thing into a little box of typically a meter by meter cube, into which you must put everything in there. It must go into space and stay there and work for a long time. So the complexity levels are extremely high. It must rely on solar cells. There is no other way of generating or giving power to anything in space. You can send in batteries, of course, but batteries are long, short life. You really don't get batteries for a long time. Nuclear reactors are not allowed into space. So essentially, you are dependent on solar power for everything you do, and you need to make sure that your solar cells generate everything that you need. So power is not so easy to get in space. If you find something on space, one of the things that ISRO fights with you about is the power. They would like you to use minimum possible power to do whatever you want to do. The launch itself is extremely violent. You can imagine you sit in a car which goes from 0 to 60, if it goes in a couple of minutes, you feel a jerk. This satellite goes from 0 kilometers per second to 11 kilometers per second in a matter of about 15 minutes. So the launch itself, or the acceleration, is so much that if you don't take special care, it will essentially break most of the instruments just in the process of launching it into space. Even if you go out in an afternoon sun, the sun feels quite hot. The poor satellite sees the sun without any protection of the atmosphere, no cloud covers, nothing. It must directly take the sun on its face. And when it takes the sun directly on its face, it really can become very, very hot. On the other hand, typical satellite goes around the Earth in a matter of an hour and a half or so. When you're in the Earth shadow space, Earth shadow, you cool as quickly as you warm up when you're in the sun. So the temperature variations can become very dramatic when you are talking about a satellite platform. It takes an intense radiation apart from sunlight. You get a lot of discharge particle, nuclear reactor kind of charged particles in space, which you have to face. The radiation level is almost as if you're sitting inside a nuclear reactor, so those kind of radiations is something that you have to protect your satellite against. A satellite obviously cannot be repaired. Over the hundreds of satellites that human beings have launched over the last 50 years or so, only one has been repaired. And one has been repaired twice actually, which is the Hubble Space Shuttle, Hubble Space Telescope, and of course people have been going to the space station. But essentially, going on to a satellite and repairing it is something that is prohibitively expensive. It's typically cheaper to fly a new satellite than to repair an old one. So your satellite must go through all these violence, must face all these environmental difficulties and still work for 10-15 years without any maintenance, without any repairs, without any hope of doing anything other than some software patching here and there. And yet, in spite of all these difficulties, a good satellite is a very powerful object to have in space because you can do phenomenal things with that. Just to briefly tell you about the space program of ours, we have had a series of rockets made for us to launch satellite. SLV-3, the satellite launch vehicle number 3, was the first satellite India flew, on which India flew a payload of our own. No any satellite was put on that. 17-ton, 23-meter height, and the smallest satellite to go up in space, 45 kilometers. Since then, we have progressed a lot. The same satellite launch vehicle was augmented, so it's called augmented satellite launch vehicle, 2 extra booster rockets. It allowed us to fly up to 45 kgs, 150 kgs into space, and that worked for a reasonable time. These two, PSLV and GSLV, and now the new version of GSLV called GSLV Mark III, are essentially the workhorses of Indian space program. The Geostationary Satellite Launch Vehicle, GSLV, is the heaviest rocket so far. Now Mark III, which will fly later this year, will in fact be 50% more heavy. But at 400 ton, 49 meters, it can carry a 2-ton satellite deep into space. And it is designed specifically for putting satellites in communication orbit. What is called this geotransfer orbit is the satellite is put in an orbit in such a way that it can eventually be taken 36,000 kilometers from here and parked in the communication link that is required, from which the satellite will essentially rotate around, revolve around the Earth in 24 hours, and just as the Earth itself spins in 24 hours, essentially that satellite appears stationary to you, and therefore you get this communication satellite, because in space it's always at one place. You can point your antennas, send your signal there, get them back over here, and therefore these geostationary satellites are the communication satellites, and that makes the backbone of our entire communication network. Polar satellite launch vehicles, on the other hand, are also very precious, very useful, and very powerful set of objects. They are slightly smaller in the sense that they are, apart from being 290 or 300 tons, the capability as far as weight is concerned is also slightly less, but they're probably the most used rockets of India's space inventory. Our moon mission, Chandrayaan, went on one of these PSLVs. PSLV, by definition, is a polar satellite launch vehicle, and its job is to put a satellite which does not go for communication, but which goes from North Pole to South Pole and continues to rotate. So as the Earth underneath turns, the satellite that is going North Pole to South Pole just has to look down, and the Earth keeps spinning underneath. The result is that the satellite will see all parts of the world without having to go anywhere. It just keeps looking down, the Earth underneath keeps spinning, and therefore it can see all parts of the world over a sustained period of time. So these PSLV launch vehicles were designed or are designed specifically to launch satellites into this polar orbit, from which they can do wonderful Earth observations. And in fact, Indian remote sensing satellites are among the finest in the world. In commercial, in non-security environment, they are by far the highest resolution images you can get, and you can buy them from a big corporation at a reasonable cost, and they can give you image of any part of the world, depending on the requirement and appropriate willingness to pay the price. But that's been one of our great commercial successes of the space program, because you can do this communication satellite. So let's look at what a launch. The rocket, like I said, costs 250 crores of rupees. Okay, the 250 crore rupee rocket works only for 15 minutes. It lives or dies within 15 minutes, and this is what a launch